A train just did something no train has ever done. In 5.3 seconds, it went from a dead stop to 800 kilometers an hour, faster than most passenger jets even reach after takeoff. This happened on a test track in China, and it is the clearest sign yet that a train capable of 1,000 kilometers an hour is no longer a concept on paper. It is being built right now. If this technology scales the way engineers say it will, the 4.5-hour trip from Beijing to Shanghai could shrink to under 2 hours, faster than flying once you count the airport. Japan is watching, Germany is watching, the airline industry is watching. In the next few minutes, you will find out exactly what China has built, what part of this is already real, what is still years away, and why 2026 turned into the year this project stopped being a rumor. Subscribe to this channel right now, because this technology is moving faster than the headlines can keep up with. China's rail engineers have spent the last 2 decades building the largest high-speed network on the planet. More than 50,000 kilometers of track, connecting megacities that used to take a full day to travel between. But somewhere in the mountains of Shaanxi province, away from the bullet trains everyone already knows about, a completely different machine has been quietly rewriting what a train is even allowed to do. It is called Tflight, and it does not run on rails in the way you are picturing. It floats. It is built by the China Aerospace Science and Industry Corporation, the same state-run giant behind China's missile and rocket programs. And that detail matters more than it sounds. This is not a railway company trying to go faster. This is an aerospace company that decided a train should behave like a spacecraft skimming through a near vacuum. Here is the basic idea. Take a maglev train, the kind that floats above the track using magnetic force instead of wheels, so there is almost zero friction. Then put that train inside a sealed tube and pump most of the air out of it. Without wheels grinding against rail and without a wall of air pushing back against the nose of the train, there is almost nothing left to slow it down. That is the entire secret behind Tflight's target top speed of 1,000 kilometers an hour. And engineers on the project have openly discussed a theoretical ceiling as high as 4,000 kilometers an hour if later phases succeed. To put that in perspective, a Boeing 737 cruises at around 840 kilometers an hour. This train, on paper, is designed to eventually beat that speed while never leaving the ground. The levitation itself relies on one of 2 approaches engineers have refined over decades. Electromagnetic suspension uses magnets on the train that are pulled upward toward a ferromagnetic rail, lifting the vehicle just a few millimeters off the guideway and holding it there through constant electronic adjustment. Electrodynamic suspension works differently, using superconducting magnets that repel coils built into the track itself, pushing the vehicle several inches higher and creating a more stable cushion at extreme speed. Once the train is floating, alternating magnetic fields along the guideway pull and push it forward in a continuous wave, the same basic principle used to launch payloads on electromagnetic rail systems. Because nothing is touching, there is no mechanical wear, no grinding steel wheels, and almost no friction left to fight against. Construction on the first full-scale test line began in April 2022, in a stretch of Yangao County in Shaanxi province, and by November 2023, that section was complete. In February 2024, the vehicle hit 623 kilometers an hour on a short test track just under 2 kilometers long, a record for this specific low-vacuum tube design. By that October, engineers successfully ran the vehicle under actual low-vacuum conditions for the first time, confirming that the speed and the suspension height both match their predicted values. State media reported that milestone as proof the physics behind the concept actually works outside a simulation. That was Phase 1. It was designed to prove the system could function at all. Phase 2 is the one everyone is actually excited about because Phase 2 is where the number 1,000 kilometers an hour becomes a real target instead of a theory. Engineers plan to test the full design speed on a track roughly 60 kilometers long enough for the vehicle to actually reach and hold that velocity instead of just touching it for a fraction of a second. If that phase succeeds, a third and far more speculative phase would attempt to push toward 2,000, and eventually that 4,000 kilometer an hour ceiling. Now here is where the story jumps forward to right now, to the reason this project suddenly became impossible to ignore. Just this month, a separate but closely related Chinese research team achieved something that made headlines across the entire rail industry. At the Donghu Laboratory in Hubei province, an experimental maglev vehicle weighing a little over 1 metric ton accelerated from a complete stop to 800 kilometers an hour in just 5.3 seconds, on a specially built 1-kilometer test track using permanent magnet propulsion. That is not a typo. 5.3 seconds. For comparison, most sports cars need that same amount of time just to reach 100 kilometers an hour. This vehicle used it to reach 800. Researchers were careful to point out that this specific platform is not designed for passengers yet. It is a proof of concept for propulsion and acceleration technology, not a finished train you will be able to book a ticket on next year. But the acceleration numbers alone reset expectations for what Chinese maglev research is capable of producing on a compressed timeline. And it is exactly the kind of result that turns a niche engineering story into global news. Within days of that Hubei test, engineering publications across Europe and North America that rarely cover Chinese rail projects were suddenly running the story on their front pages. Railway trade journals that normally report on ridership statistics and signaling upgrades were instead publishing acceleration curves and comparing them to fighter jet catapult launches. That reaction is exactly why this particular test mattered so much. It was not just a Chinese state media announcement being repeated. It was independent rail engineers outside the country looking at the raw numbers and admitting that nothing else currently in development anywhere on Earth comes close to matching it. So why does this all matter beyond the impressive numbers? Because China is not only building one experimental super train, it is running an entire portfolio of speed projects at the same time. And each one is chipping away at a different part of the same problem. Start with what is already running today. The Shanghai Maglev has been carrying paying passengers since 2004 using German-developed technology, reaching a top operational speed of 431 kilometers an hour on its short run connecting Pudong Airport to the edge of the city. For more than 20 years, it has held the title of the fastest commercial train on Earth. And almost nobody outside China talks about it, mostly because the line itself is short and mainly used by travelers heading to or from the airport. Then there is the CR450, a completely different kind of train. Unlike Tflight, the CR450 does not levitate. It rides on conventional steel wheels, which means it can use existing high-speed rail infrastructure instead of requiring an entirely new sealed tube system. Throughout 2026, CR450 prototypes have been running intensive trials, and the project represents China's attempt to push traditional wheeled rail as close to its physical limit as engineering allows, before magnetic levitation becomes strictly necessary. And sitting between those two approaches is a third project from CRRC, China's main train manufacturer, which unveiled its own 600 km an hour Maglev train in the summer of 2025. That train is explicitly designed to fill the gap between conventional high-speed rail, which tops out around 350 km an hour, and commercial air travel, which cruises somewhere between 900 and 1,000 km an hour. 3 different speed classes, 3 different technologies, all developed inside the same country within a few years of each other. This is the part most coverage of the Tflight project leaves out. China is not betting everything on one science fiction train reaching 1,000 kilometers an hour and hoping it works. It is building a ladder with the 600-kilometer-an-hour Maglev as one rung, the wheeled CR450 as another, and Tflight sitting at the very top as the long-term, high-risk, high-reward research project. If any single piece underperforms, the country still ends up with a faster rail network than it has today. Look specifically at the route everyone keeps bringing up, Beijing to Shanghai. On today's conventional high-speed rail, that journey covers roughly 1,300 kilometers and takes about 4.5 hours on the fastest scheduled services. A functioning 600-kilometer-an-hour Maglev could realistically cut that closer to 2.5 hours. If engineers ever get a full Tflight corridor built and running near its design speed, industry estimates put the same trip at somewhere close to 90 minutes, gate to gate, without the security lines, boarding delays, and taxi time that come with flying. That is the number that keeps showing up in Chinese planning documents. And it is the number that would genuinely make short-haul domestic flights between major Chinese cities almost pointless to book. Now let's talk about why this technology is genuinely difficult. Because the honest version of this story includes the obstacles, not just the highlight reel. Building a sealed, low-vacuum tube across 60 kilometers, let alone the eventual distances needed to connect major cities, is an enormous engineering and financial undertaking. You are not just laying track. You are constructing a continuous airtight structure across hills, rivers, and populated land, and keeping the pressure inside consistently low across the entire length. Professor Andrew McNaughton, a rail infrastructure specialist who has reviewed Maglev projects internationally, has pointed out that both construction and operating costs for vacuum Maglev systems run substantially higher than conventional high-speed rail, and that the technology only makes financial sense in corridors with enough population density and travel demand to justify the price tag. Then there is the safety question, which engineers cannot avoid no matter how good the propulsion numbers look. What happens if a tube loses pressure while a train is moving through it at 900 kilometers an hour? How do you evacuate passengers safely from a sealed vacuum environment? How do stations handle pressurizing and depressurizing sections of track without slowing the entire system down? These are not reasons to dismiss the project, but they are exactly why China has spent years running short test segments before committing to anything close to a full commercial corridor. And here is something the flashiest headlines about this story consistently get wrong. As of right now, the Chinese government has not confirmed a commercial rollout date for a passenger-ready 1,000-kilometer-an-hour Maglev line. What has happened in 2026 is a wave of test milestones, record-breaking demonstrations, and expanded trial infrastructure. Not a ribbon cutting on a route the public can book. The honest way to describe 2026 is the year the testing phase became undeniable, not the year commercial service began. That distinction matters if you actually want to understand where this technology stands instead of just reacting to a headline. So, what does the realistic timeline actually look like? Phase 2, testing on the full 60-kilometer track, where the vehicle is meant to actually sustain 1,000 kilometers an hour rather than briefly touch it, is the next major checkpoint engineers and industry analysts are watching closely. Success there would be the strongest evidence yet that a commercial version is genuinely feasible within this decade. Failure, or a series of delays, would not be surprising either, because almost every Hyperloop-style vacuum tube project attempted outside China has struggled to get past small-scale prototypes. American ventures, built around similar vacuum tube concepts, burned through hundreds of millions of dollars before folding entirely, unable to solve the same cost and infrastructure problems China is now trying to work through with state backing and a much longer financial runway. That is really the core difference between China's attempt and every failed Hyperloop project that came before it. Previous attempts, mostly funded by private investors expecting a return within a few years, ran out of money before the engineering problems were solved. China's version is being developed by a state-owned aerospace contractor with defense-level funding patience and a government that has already proven, through 50,000 kilometers of conventional high-speed rail, that it is willing to build transportation infrastructure at a scale no other country attempts. It also is not happening in isolation. Japan has been developing its own superconducting maglev for decades, the Shinkansen, designed to connect Tokyo and Osaka at up to 505 kilometers an hour. That project was originally targeting a 2027 opening for its first section between Tokyo and Nagoya. But tunnel construction delays and local disputes over environmental impact have pushed that date back with no confirmed new opening year. For the first time in the history of high-speed maglev development, Japan is no longer the country setting the pace. China is. None of this comes cheap, and China has never pretended otherwise. Building 50,000 kilometers of conventional high-speed rail already cost hundreds of billions of dollars over 2 decades. And vacuum tube maglev infrastructure is significantly more expensive per kilometer than the steel-wheeled network it would eventually sit alongside. What makes this project different from a private startup burning through venture capital is that it is backed by the same government financing model that built the existing rail network, funded as a long-term state infrastructure rather than a business expected to turn a profit within a few fiscal quarters. That patience is the real advantage China has over every rival Hyperloop program on Earth. India has announced plans to begin its own Hyperloop-style research, starting in 2026. Switzerland and the Netherlands are both running early feasibility studies on vacuum tube transport. None of them are remotely close to China's current test results. Industry figures outside China have started describing this openly. The head of one prominent international Hyperloop company said China's progress is proof that vacuum tube transportation is not a distant fantasy anymore. It is becoming an engineering reality years ahead of schedule. And competitors everywhere are now racing to catch up to a head start they did not expect China to build this quickly. There is a question almost nobody asks in the middle of all this excitement, which is what actually riding at these speeds would feel like. Because the train is floating rather than rolling, and because acceleration is applied gradually through a continuous magnetic wave rather than a sudden jolt. Engineers involved in maglev design have consistently said the sensation is closer to being in a smoothly climbing aircraft than a train picking up speed on a track. There is no wheel noise, no rail joints clicking underneath you, and because the tube removes most of the air resistance, there is very little turbulence-related vibration either. The bigger engineering challenge is not comfort at cruising speed, it is managing the pressure change as the train enters and exits sealed sections and making sure acceleration and deceleration stay gradual enough that standing passengers or anyone without a seatbelt would not be thrown off balance. There is also an environmental angle that rarely gets attention in the excitement over top speed numbers. A maglev route connecting major cities at close to airline speed, but running on electricity instead of jet fuel, would offer similar door-to-door travel times, with a dramatically smaller carbon footprint. For a country the size of China, shifting even a portion of domestic air travel between megacities onto an electrified, high-speed ground network is not just a transportation upgrade. It is a climate strategy with a very visible, very marketable centerpiece. So, where does that leave the actual question everyone watching this story wants answered? Is a real working 1,000 km/h maglev train actually coming? Based on everything currently on the record, the honest answer is this. The core physics has already been demonstrated on short test tracks. The propulsion technology has already produced world record acceleration numbers this year alone. The infrastructure for sustained high-speed testing is currently under construction. What has not yet happened is a commercial passenger line running at that speed over any meaningful distance, and no government official has put a confirmed date on when that will change. What makes this story different from 100 other speculative future tech headlines is that China has already built and tested the hardware in the real world, not in a rendering, or a press release. Test tracks exist. Vehicles have moved. Speed records have been set and then broken again within the same year. That puts this project in a completely different category than the Hyperloop concepts that came before it and quietly disappeared. The next major checkpoint to watch is whether engineers can sustain 1,000 kilometers an hour across that longer 60-kilometer track, not just touch it briefly the way earlier tests have. When that happens, and if it happens, the conversation shifts from whether this technology works to how quickly China can afford to build it between its actual cities. It is worth stepping back and remembering how quickly this entire field has moved. A decade ago, vacuum tube transportation was mostly associated with a single American billionaire's white paper and a handful of startups that never got past a few hundred meters of test track before running out of funding. Today, a state-backed aerospace contractor in China has full-scale test infrastructure, multiple independently verified speed records set within the same calendar year, and a second, longer track already planned for the next phase of testing. That is not incremental progress. That is a field that spent years stuck in place and then suddenly started moving at the exact speed its name always promised. None of this means a public 1,000 km an hour Maglev ticket is going on sale next year. It almost certainly is not. What it does mean is that the hardest part, proving the physics can survive contact with reality, has already happened. On camera, on a real track, more than once. Every prior attempt at this idea, anywhere in the world, failed before reaching that point. China has already passed it. So the real story here is not a single shocking headline number. It is a pattern. 3 separate speed classes of train being developed at the same time inside one country. A world record broken this month on a platform explicitly built to push past the last one. A rival Maglev program in Japan slipping further behind schedule while this one keeps hitting its targets. Watch this space closely because the next test track being built right now in China is longer than the last one, and every time these engineers add distance to the track, they get closer to proving that 1,000 kilometers an hour on the ground is not a headline anymore. It is a schedule.